Okay, guys, Math 192. We're going to look at Activity 32, talking about counting principles and probability here. So let's just dive in here. So the first example here is talking about Hogwarts School of Witchcraft and Wizardry is hosting a wizard tournament. 3 students from Hufflepuff, 4 students from Ravenclaw, 6 students from Gryffindor, and 2 students from Slytherin will have entered their names in the Goblet of Fire. The Goblet of Fire chooses 2 students at random, one after the other, without replacement, to participate in a particular event. On a separate sheet of paper, whether it be typing paper or regular paper, doesn't matter. We're going to draw a probability tree for this experiment. Okay, so I'm just going to go down here to this problem, and so we have the Goblet of Fire here. Yeah, goblet. That looks like a goblet, right? It's awesome looking. Put some jewels on it. Make it pretty looking. Goblet of Fire. I don't know if I called correctly in the film. It is Blue Flames. I'm not sure if that really is or not. Okay, so here's what can happen with the probability tree. So we have the first student is chosen. So that first choice is coming from all of the students involved. So we had 3 from Hufflepuff, 4 from Ravenclaw, 6 from Gryffindor. So 3, 4, 6, and 2. So 3 from Hufflepuff, 4 from Ravenclaw, 6 from Gryffindor, and 2 from Slytherin. So I'm just going to note them as H's for Hufflepuff, R's for Ravenclaw, G for Gryffindor, and S for that. So when that first student is chosen, we've got the Hufflepuff 1, Hufflepuff 2, Hufflepuff 3. Then you got Ravenclaw 1, Ravenclaw 2, Ravenclaw 3, Ravenclaw 4, got Gryffindor 1, Gryffindor 2, Gryffindor 3, Gryffindor 4, Gryffindor 5, Gryffindor 6, and then the 2 from Slytherin. I'll put those over S2 and S1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 choices there. Okay, so what's going to happen? So what's the probability for each one of these people out of that? Well, it's 1 out of 15 for the first person, for all 15 wizards or witches, whichever one it is. Okay, 1 out of 15 for that first choice. And then when you go to your second choice, your tree is going to have everybody, each one of these individual nodes here. If S1 is chosen, then you're going to have 14 choices. So 14 choices on each one. Okay, so each person on this round has a 1 in 14 shot. And you would have that for each one of those. Okay, I'm not going to be picky about you drawing out that probability tree there. Okay, so when you look at the problem here, okay, it says B part says, what is the probability that 2 students selected are from Hufflepuff? Okay, so what's the probability of the first person selected being from Hufflepuff? 3 out of 15. And then the second person being drawn, if you drew a Hufflepuff to begin with on the first choice, there's only 2 Hufflepuffs left. But now there are only 14 people in the drawing. So then we multiply. 3 times 2 is 6. 15 times 14. Let's get a little help with that. everybody knows the 14's times table. 210, and then we're going to reduce that. 6 over 210. Math, enter. 1 over 35. To the decimal, 0.0 to 3 decimal places. So we'll go with. All right, C part. What's the probability that one of the students is from Gryffindor and the other is from Slytherin? Show any necessary calculations. Okay, so Gryffindor, and then the other from Slytherin. It doesn't say which one gets chosen first out of that. So, how many are from Gryffindor? Well, we have 6 from Gryffindor, so that's 6 out of 15. And how many from Slytherin? There were only 2 names in the goblet from Slytherin, so that's 2 out of 14. And we don't have to worry about order here because if the person from Slytherin was chosen first, they would be 2 out of 15, and the second choice was 6 out of 14. It doesn't matter what order there, because really the math that's happening, no matter which way it happens, is with this, and we know that the top part is the multiplication is commutative, so it doesn't matter which order the 6 or the 2 comes in, but we do have to have 15 and 14 in the bottom, so that's going to be 12 over 210 out of that, and we can reduce that. It should be 2 out of 35, I would think. 12 out of 210. 0.057. Again, reduced fraction and decimal to 3 decimal places. What's the probability that neither student is from Ravenclaw? So show any necessary calculations. Okay, so neither of those can be from Ravenclaw. So how many are non-Ravenclaws in the problem? So Ravenclaw had 4 choices, so there were 15 total. So we could have 11 out of 15 for the first choice, and then so we choose someone that is not in Ravenclaw for the first choice. We need to choose 10 out of 14 in the second choice, and multiply those together. I'm going to do a little bit of cross canceling here because I can. That'd be 22 over 30 plus 12 would be 42. Now then I'll reduce that to 11 over 21. Get the decimal approximation for that. 55 to 4. 3 decimal places out of that. So these are the people that are not in Ravenclaw. That's who we're choosing. 11 of the wizards or witches are not in Ravenclaw. You choose one of those, then there are only 10 that are not. Okay. What's the probability that the first student selected is from Ravenclaw? And then show any necessary collection. So first student from Ravenclaw would be 4 out of 15. And then the second student, it doesn't matter what where they're from, okay? Just as long as the first one is from Ravenclaw. So the others could be 14 out of 15 for those. It doesn't matter what the second one is. So multiply those together. 4 times 14. 56, and then 15, and I did that wrong. That should be 14 out of 14, which reduces to be 1. And then so we have 4 out of 15, which is approximately 0.26. And we'll do the repeating decimal there because it does repeat. It's a more accurate solution to that. Okay. Wizards and Wizardry. My son has been enamored with Harry Potter lately. We let him watch a little bit of that, and he has become a wand spinner. He likes to uh, pretend he is Harry Potter. So it's a pretty funny Snape impression that he has. So let's move on. So moving on, Michelle's drawn 3 cards from a special deck consisting of 10 blue cards, uh, 10 blue cards, and 12 orange cards. 10 blue, 12 orange, 22 total. Okay. So probability tree, you should be able to draw that. That when you draw that probability, you got a blue and an orange, and then there are 10 of those, and there are 12 of those. So there's 10 out of 22 probability there, 12 out of 22 probability there, and then the second draw, you could have blue and orange. Again, without replacement. So now the second draw, if you drew a blue to begin with, you only have 9 out of 21. If you drew a blue and then an orange, you still have 12 out of 21. And in the second draw, if you draw blue, you're going to have a probability of, if the first draw was orange, then you still have all 10 blues. And if you draw an orange, you have 11 oranges left. 21 is what those both are supposed to say there. 21. Okay. And then the third draw takes that. It says, okay, well, now if you draw blue again, you only have 8 out of 20. And if you draw an orange, you have blue, blue, blue. So you still have all the oranges out of 20. And if you draw an orange the second time, you already drawn one blue, so that's 9 out of 20 there. And then you draw an orange there, you've drawn 11 out of 20 there. And you keep going with that. Okay, so separate sheet of paper, you do that, build that probability. So you got to just follow it down the chain and reduce that color on the numerator, and always reduce the denominator by 1 each time with each draw. Okay, what's the probability that all 3 cards are orange? So that'd be the first one, probability is 12 out of 22, right? The second one, you've already drawn 1 orange card, so there's 11 left. There's 21 cards in the deck now. And then the third one, we have 10 orange cards and 20 cards left. And we're going to reduce this. I'm going to do some cross canceling, make that easier. And then I'm going to cross cancel the 2 with the 12. Make that 6. And this becomes a 1 and a 3. So 3 over 21 probability, which 3 over 21 reduces to 1 over 7, which is a decimal, would be 0.143. Okay. What's the probability that one of the cards drawn is blue? Show any necessary calculation. Okay, so we got to deal with order of draw here. So probability that one of the cards is blue. Probability on the first draw of being blue would be 10 out of 22. And then the second card, let's say, all right, so we got different scenarios that can happen. So we could have blue, orange, orange. We could have blue, orange, blue. We could have blue, blue, blue. Or we can have blue, blue, orange. Okay, those are the things that could happen where we have a blue there. But we could also draw cards that are orange, 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 or orange, orange, blue. or orange, blue, orange, or orange, blue, blue. And then we could do orange. Let's see. I don't think we have. Let's see. We got blue in the first position with orange and orange. Blue in the first position with orange and blue. Blue in the first position with blue and orange, or blue, blue, blue. We could have orange, orange, blue, orange, blue, orange. We've already done blue, orange, orange, so we could have orange, blue, blue. Okay, so we've got to find probabilities of each of these things and then add them all together. Then, okay, probability that only one of the cards is blue. So which ones of those have only one card that is blue? This one, and this one. Okay, so we need all three of those added together for that. So blue, orange, orange, probability for blue, orange, orange would be 10 out of 22 times orange, orange would be 12 out of 21, 11 out of 21, 20. You multiply that all together. And I'm simplifying here. A long way to get 1 over 7. And then we're going to do orange, blue, orange. That'd be 12 out of 22 times 10 out of 21 times 11 out of 20. Okay. Notice those are the same numbers on the top, just in a different order, and the same numbers in the bottom. Okay, I know this is going to reduce to be 1/7 as well. Okay. And then we have orange, orange, blue that we need to do. So orange, orange would be 12 over 22, 11 over 21, and then blue, 10 over 20 at the end. Again, same thing, 1/7. Add those together, 3/7. The decimal approximation. 0.429. Part D. What's the probability that more blue cards drawn than there are orange cards drawn? Show the necessary calculations. Okay, so we got to think of the scenarios where more blues are drawn. So you could have all blues drawn. That's an option. We could have, and so that would be 10 out of 22, 9 out of 21, 8 out of 20. And then you could have 2 blues and an orange in that order. So that'd be 10 out of 22 times 9 out of 21 times 12 out of 20. Different numbers there. Or you could have blue, orange, blue. It'd be 10 out of 22, 12 out of 21, and 9 out of 20. And then you could have orange and then 2 blues. It'd be 12 out of 22, and then 10 out of 21, 9 out of 20. Those are the 3 scenarios where more blue cards are drawn than red cards. Orange cards. Okay, so let's calculate these up here. We'll cross cancel here. Be 6 over 77. Blue, blue, orange. So here we could do 10 and 20. And here we could do 21 and 7. This becomes a 2. And then that becomes a 1 and 11. So it would be 9 over 77. This one has the same numbers involved on top and bottom, so it's the same value. And this one has those same numbers involved. So 9 is 27, and 6 would be 33 out of 77, which reduces to 3/7. Which we said earlier was 0.421. So we have probability of drawing more blue cards than orange cards. Okay. So probability there, you've got to think a little bit differently. Kind of think about your scenarios of things that could happen for the case that they're looking at. All right.